Hello everyone, my name is Dimitrios Vassiliadis and I work as a space weather scientist at NOAA in its Satellite and Data Service. Today I will talk to you about satellites and some of the many problems they face due to space weather. Indeed, we're so reliant on satellites today, what with telecommunications, phone, television, internet, GPS for our cars, planes and other vehicles, Earth observing constellations and many other services, that we often take satellites for granted and forget that they too can be vulnerable since they operate in a harsh and unforgiving environment, which is space. So let's find out what the weather in space is like. First, what is space weather? We call space weather the sum total of all the processes that can damage, or worse, can permanently take out of commission not only satellites, but also other structures in space, and with them, take down the services that these satellites deliver to us. So for spacecraft, space weather means powerful strikes from fast-moving tiny subatomic particles, electrons and protons, and/or static buildup produced in the satellite exterior or body. Think of them as hail that can damage your car's roof or that can go through your greenhouse roof and damage your expensive flower pots inside. In addition to those particle effects, space weather is all about other problems, for example, altering certain signals that the satellites receive and emit, such as GPS signals, but we will cover them in a separate talk. Also, we will differentiate space weather by the location in which it takes place. For terrestrial weather, we distinguish between polar weather, weather in the tropics, etc. Similarly, the weather we'll discuss today will be weather in certain regions in space near Earth, where the orbits of the satellites and the space station are. These regions are called the Earth's magnetosphere and ionosphere, and so we'll not discuss, for example, weather in interplanetary space or space weather effects on Earth's surface and crust. So space weather originates ultimately and mainly at the sun. Solar flares are sudden explosions high up in the solar atmosphere that can produce large numbers of particles very quickly and deliver them in the exterior of the star. The particles start traveling away from the star and they will strike whatever it is in their path. Sometimes spacecraft orbiting the Earth can be found on that path, and in that case, sensitive electronics on board the spacecraft can be struck by particles. Let me show you what it looks like when those electronics are part of a telescope designed to observe the sun. When the particles arrive, they impact the telescope's light-collecting plate and they appear on the solar image like snow. Thankfully, that damage is transient and the telescope optics recover almost as soon as the particle beams have passed through. Now, we're showing a different set of solar storms from a very busy interval of active solar wind conditions at the end of 2003 that was dubbed the Halloween storms because it happened right around the end of November of that year. At that time, several disturbances took place on the sun and its atmosphere. Each one of those unleashed beams of energetic particles, which we now know as electrons and ions, that impacted a large number of spacecraft and caused disruptions on other technological systems, mainly in space, but also on the ground. Issues included effects on about 60% of NASA's space science missions, the loss of contact with the ADIOS 2 satellite, the safing of the DRTS satellite, and many more. And on the right, I'm showing an example of the more benign effects of space weather, such as the auroral displays in the north, the aurora borealis, and the ones in the south, aurora australis. But not everything is benign when it comes to space weather effects. The problems are not limited to electronics and telescopes. Particle radiation can interact with biological matter, and it can break molecular bonds and cause damage at the cellular, tissue, and over time even at the organ levels. Astronauts are susceptible to solar particle radiation because the space station provides very specific options for their protection. During solar active conditions, they have to shelter in radiation-blocking compartments of the station, but even there is a chance that a small amount of radiation will penetrate the walls. To give you some context, astronauts who spend 3 times in the ISS, the International Space Station, will be subjected to over 3 times the maximum recommended dosage of radiation for 1 year for a health worker. In addition to astronauts, airline pilots and other crew members are exposed to the same particle radiation if the flight takes them too close to the Earth's North Pole. This is because near the Earth and South Poles, the Earth's magnetic field, which normally hinders and shields us from solar energetic particles and shields us from their effects, allows those particles to reach aircraft altitudes and even closer to the Earth's surface. Thankfully, passengers are not at risk, even frequent flyers. However, this remains a concern for airline crews almost as much as for astronauts. Let's switch now to a different type of particle radiation, that occurs in the magnetosphere. Solar energetic particles are not the only type of particle radiation in space weather. A second major paradigm, much closer to us, can originate at our own planet, the Earth, thanks to its magnetic field. The field can produce and sustain energetic particles that can impact electronics as well. The outermost part of the Earth's environment the Earth's upper atmosphere is the magnetosphere, where the magnetic field of the planet can trap particles. These particles, are typically electrons, but in some cases they can also be protons, and they originate mainly in the magnetosphere itself or in lower layers. The magnetosphere is a very dynamic place, as you can see from this animation on my right, and it's continually expanding and contracting, accumulating energy in the magnetic field and its particle populations, and then releasing it explosively. Once particles are trapped in the inner magnetosphere, they're guided to two regions in its interior, the so-called radiation belts. Let's take a look at them. Deep inside the magnetosphere are these two donut-shaped regions that are the Van Allen radiation belts. Particles trapped in those may increase their energy hundreds of times. They're mainly electrons, as mentioned earlier, but they can also include protons. Even though the percentage of these electrons that get energized is minuscule compared to the overall population of electrons in the magnetosphere, the numbers are not in the satellite designer's favor. The few but powerful electrons can impact surfaces and interiors of spacecraft and can damage electronics in ways similar to solar particles. So what do we mean by accelerating particles to high energies? Here again is a beautiful rendering by researchers in the science community, which shows the Earth in the center, surrounded by the radiation belts, and the Sun in the background, which is of course ultimately the cause of this activity. Particles can be energized in several different ways in that volume of space, the radiation belts, and then they remain trapped there until they slowly decay away. During that time, they can wreak havoc on satellites that pass through that region. For context, the situation is similar to what we have in a particle accelerator, a storage ring, where particles are energized and stored. As we see in this picture, particle radiation is produced and trapped in the belts, where it continues to increase, both in numbers of particles, what we technically call the flux, and in the energy that the average particle carries. The longer the event lasts, the more of these energetic particles get produced, and the higher energy each one carries contributes to the risk. The particles can inflict risk on satellite electronics, solar panels, and other components. For a comparison, we show two storage rings, two underground particle accelerators that have similarities with the actual accelerator that we have in space above our heads. The process, of course, is not exactly the same. The accelerators designed by humans are much more well-defined, whereas nature is messy. There, in the radiation belts, acceleration takes place via waves, linear and nonlinear impulses, and the process is much less efficient. But the numbers of particles of the starter population are staggeringly high compared to the handful of particles in a human-produced accelerator. So this is a complicated interaction between particles and electromagnetic waves of several different types. Now, here is another view of radiation belt storms. Interestingly, these types of storms are more prevalent away from solar maximum. So while during solar maximum we have high flux of solar energetic particles, when the solar cycle continues past its maximum, we have these different recurring storms, as you can see, one after the other, where solar energetic particles may be fewer, but conditions are ripe for magnetospheric particles to be energized and do their damage. You can see these coming one after the other at about 27 days. This is the solar rotation, and they behave like a clockwork. Thankfully, the solar minimum is a time when both types of particles, both solar and magnetospheric, are at their lowest point. As a historical note, this cosmic accelerator was one of the earliest discoveries in a series of rocket and satellite launches, notably Explorer 1, by Professor James Van Allen and co-workers. This was an important milestone in space physics, and the mechanisms that are involved are still not fully elucidated even to our days. They're subject of open research. Now, you would say, are particle radiation effects limited to just Earth? Not at all. These cosmic accelerators are found in every other magnetized environment and every other magnetized planet. So, for example, in Jupiter and Saturn, we have vast trapping regions where such particles can develop and get energized. In contrast, Moon and Mars do not have a magnetic shield to protect them from the solar radiation, and thus are subject just to the solar component. Since this is a space weather talk, I would like to cover the actual process by which these particular fast-moving particles damage the electronics or the biological tissue that we mentioned earlier. So for now, we'll just concentrate on non-biological materials, but the analogy with human tissue is there as well. There are 4 different types of processes in which radiation can produce damage. 2 of them involve electrostatic discharges. The top you see surface charging, which is when the particles that come from above in this rendering do not actually have enough energy to go through the material, but they deposit their charge on the surface and they do damage locally. In contrast, internal charging takes place when particles are energetic enough to go through the material and deposit their energy and do damage internally. And on the lower right is a picture of an actual component from a spacecraft by ESA, where arcing produced by these discharges damaged locally part of the electronics. Here are 2 additional spacecraft charging mechanisms. We have a single event upset situation, as shown in the upper right, where hardware or software faults are produced by sudden, very large amplitude charging events, and this may involve both surface and internal charging. In some cases, that creates phantom commands in which either the operating system or individual applications of software suffer some damage. On the other hand, we can have total ionizing dose, or TID, which is the effect of slowly accumulating damages, probably over months and years, basically due to many surface charging or internal charging incidents. The total ionizing dose is calculated as a function of the material that is subjected to these radiation damages. Now let's take a look at what the National Oceanic and Atmospheric Administration undertakes to reduce the risks related to spacecraft charging and other types of space weather. NOAA monitors these events and issues alerts or nowcasts, warnings, and watches. It also issues forecasts when there is a sufficiently long lead time and high likelihood of an event occurring. The forecast office that you see in the lower left is a central facility within NOAA's Space Weather Prediction Center, or SWIPSI, which monitors conditions along with other domestic and international weather agencies. SWIPSI monitors the most important solar wind, magnetospheric, and other conditions prior to any events, and then it issues forecasts and nowcasts. It generates several different particle radiation products and dashboards for a very wide range of space weather information users. In addition, preparations are not limited to just observations and data taking. NOAA also utilizes models of the space environment, which are adapted from models developed by the research community. Among them, relevant to the radiation belts, is the relativistic electron forecast model, or REFM, a snapshot of which we see here. And that represents particle fluxes at geosynchronous orbit, shown as the green squares, whereas the model predictions are shown as the yellow diamonds. In addition to this and other operational, fast executing models, there are also much more sophisticated research to operations projects. Typically, these projects start with a model developed for research purposes, such as the one shown in the lower right, and over the course of the project, this model is slowly adapted and then enters operations. So in summary, we saw that space weather can damage satellite electronics and can threaten the health of humans in space, as well as disrupt various operations both in space and on the ground. The effects take place at various locations, at the familiar GEO, LEO, orbits and also at aviation altitudes. Two main sources of particles that we've covered here are the Sun and its atmosphere and the Earth's upper atmosphere, which we discussed as the magnetosphere. And there are several types of events which take place over the solar maximum, over different parts of the solar cycle, such as the rapidly increasing fluxes of solar energetic particles and coronal mass ejections, and others take place in the descending part of the cycle, and they are the regular storms that we saw as an example. We also discussed four major types of radiation impacts, depending on their energy and the physical origin or the type of discharge. NOAA is working to monitor and forecast these activities and continues to do so in collaboration with other domestic and international agencies. Thank you for your attention.